All right, welcome everyone to the second meeting of ATiA for 2022. It's my pleasure to have Francesca Tombari give us a talk. She's currently a graduate student at KTH, and she's going to tell us about realizations of posets and tameness conditions. Take it away, Francesca.
Thank you a lot, Justin and Mike, for inviting me. It's a great opportunity in general to give a talk, but in particular because it's the first time that I have the chance to talk about this new work that I worked jointly with Wojciech Chacholski and Alvin Jean, both at KTH in the TDA group. So I'm really excited about it. And and thank you everybody for being here, of course. I'm very happy to see some familiar and less familiar faces. All right, so let me start with just a bunch of keywords. So as you might notice from some of these keywords, this is going to be a talk in persistence. But the main actor of this show is called Realization. That is not what you might think about. It's not a realization of an abstract simplicial complex. It's something else that we came up with. It has a construction for posets that transforms a poset into another poset. Why is this a talk in persistence? Because it turns out that these realizations are fits well in the context of persistence as indexing category for a persistence module. But before going to realization, I need a little bit of motivation. So I'm going to start talking about upper semilattices, and in particular, why is it convenient to use them as indexing category for a persistence module. All right, so let's get started with fireworks. So definition of tame functors, and we see it as a left-Kahn extension. So in particular, if you take a functor f indexed by a poset j, we call it tame or discretizable if it can be written, it is the left-Kahn extension of another functor g indexed by a finite poset I this time. Along a poset functor that is this small f here. So usually left-Kahn extensions are computed as co-limit, which involves universal properties, so not like the nicest beast to deal with, right? Sorry, I forgot to mention. So the landing category, I'm keeping it general and call it just C. But if you substitute this C with a category of finite dimensional vector spaces, then you just get a persistence module. So yeah, whenever you hear me talking about the tame functor or discretizable functor, discretization, just think about your favorite persistence module, and that's what I'm talking about.
Right. And sorry, Francesca, just to maybe give an example. So if I wanted to think of like the natural numbers including into R, and then thinking of like my R index persistence module as like the left-Kahn extension of one of these like in-indexed persistence modules, like that's the kind of picture you want to have in your head.
Precisely. Yes.
Okay, great, awesome.
And that's a good hint, because that's one of these examples that we're thinking about, but that's a very particular one. And realization, we'll see, generalizes a little bit this intuition.
Awesome.
All right. So yeah, that's the diagram that you might want to keep in mind, but also keep in mind the example that Justin just mentioned. And but also let me notice this fact that if you have if your discretization comes out from an upper semilattice, which is just a poset for which you can take all finite coproducts or joints. I sometimes call them coproducts, sometimes joints. I'm saying the same, it's the same thing. And if this discretizing functor, small little f, is a homomorphism, meaning that it preserves coproducts. And moreover, if your category C has an initial object, then the left can extension is computed at a point of your poset A is isomorphic to this less scary thing, which is just an evaluation of your functor G on the coproduct of downset of your point A. Actually, this is not precisely a downset, because notice that here I'm taking the downset of A intersected with the images coming from the discretizing map F, and then I take those points in I, so in the finite poset. So not precisely a downset, but sometimes it happens that this map is an inclusion, so you can actually call it downset. But yeah, this just to say that if you want to treat persistence module as left-can extension, then working with the upper semilattice is super convenient, because it allows you to have an explicit description of your module, not in terms of co-limit, but like really an evaluation on a coproduct. Okay. I need another piece of motivation still about upper semilattices, and it relates to minimal free resolutions. So if you have a functor, this time just with values on vector spaces, its minimal free end resolution is a sequence of this form where these PIs are free functors. Here, maybe this might not be a, I don't know if that's a conventional way of writing it, but here I'm saying that these vector spaces appearing here as beta I f at A, I just mentioned it, but they are just vector spaces, and they characterize your free functor. The notation is relevant for some theorems that we are going to see soon. So whenever you see this beta I f at A, think about a vector space, and they characterize your PI in the resolution of the functor. This is just an example for the ones of you who are not familiar with the free functors resolution. So just have in mind this simple example. Take the poset given by 2 layers, basically, where each of the 2 layers, so the 2 layers are fully connected, borrowing a term from neural nets. Here, the free functor is given as the direct sum of this functor that has a generator on the left bottom, and it propagates upwards following the relation in the poset. And here another generator, bottom right this time, that propagates again upwards following the relations.
So maybe just to summarize what you just said, so these like free functors at an element A, I just look at the upset at A, and then I put whatever vector space I want on that upset, and then it's constant there, and then 0 outside of that.
Perfect. Yes.
All right, great.
Exactly. Thank you. And right. Now, apparent change of topic, because I'm going to introduce you the notion of Kazoo Complex in our context. So now you need still a functor indexed by a poset into vector spaces, but this needs to be finite. We define the Kazoo complex of G at a point A as the chain complex given by for which at each degree is given by a direct sum over some subsets of parents of the point A, having a common ancestor. This direct sum is of co-limits again, of the functor G taking on some intersection of downsets. Do not concentrate too much on the details here, but maybe something that I would like you to underline is that this direct sum is taken on subsets of parents, which has a fixed size given by the degree and has a common ancestor. What I want you to notice as well is that this Kazoo complex is computed at each point of the indexing poset. And also, it happens that if I, the indexing category, is an upper semilattice, then the colimit disappears and it gets substituted by G, evaluated on a product this time, so on a meet of such sets appearing in the direct sum. So,
sorry, just to ask a clarifying question. So parents, so P of A, are those points below A?
Not only below, but such that there is nothing in the middle from the parent to A. Okay,
so they're like the covers of A. Right. I guess that's one term for it. Yeah. Okay.
Yeah. We discovered that term later.
Okay.
Than use parents, because parents is taken from graphs theory, from more combinatorics, and yeah, we took the annotation from there. But that's a cover, yeah.
Great. Yeah, that makes sense. Yep. Perfect.
All right. Keep in mind this thing of upper semilattice, of what happens when I have an upper semilattice. And now let's connect these two slides that I just presented to you together with the theorem. So if you have this functor indexed by finite poset, assume that an element inside the poset have this property of having every subset of its parents, which has a common ancestor, also has the product. Seems a little bit made up, but you'll see that in a second that it makes sense. Well, if this property holds, then for every degree I, the vector spaces beta I, J, G at A, remember those ones that characterize the resolution of G, are actually isomorphic to the homology of the Kazoo complex of G at the same point A.
Sorry, so, can I ask another question? I'm sorry, I'm just very excited because I feel like this connects a lot of constructions. So this meet of S, so is that some sort of ancestor that sits below all of those parents?
Yes, it's exactly this, but it's the maximal one.
Yeah, okay, yeah, because there could be, of course, further ones down.
Possibly, if you have, the point is that in a general poset, you might have a lot of ancestor and the maximal ones might not be unique. Mm-hmm. If it is unique, then it's called the product. Or the meet. But this makes a good connection with an observation that I want you to that I would like to make, which is that this condition is not that crazy. For example, it's satisfied for upper semilattices, because taking all the ancestors, saying that there is a maximal one means that there is a coproduct. So it gives you uniqueness of this thing. So and this is important for this corollary of the theorem, which is that if this time your functor is indexed by an infinite poset, but it is discretized by a finite poset, which is actually a finite upper semilattice, and the discretizing map is a homomorphism, then the functor is infinitely resolvable. And the only non-trivial Betty diagrams appear in the finite poset. And moreover, you can compute them by means of the homology of the Kazoo complex. One thing to notice here is that here it does not appear just the functor f, but precomposed with the discretizing functor, because we always need a finite poset in order to define the Kazoo complex, because we need to talk about parents, and in an infinite poset, you might not be. It might be that the parents are that there are no parents. So this is important, and I would just like to leave you with this takeaway, which is not that I want to avoid co-limits in my PhD life, but it's kind of the reason. But what I want you to notice is that if you work with tame functors and indexed by upper semilattices, then you can easily relate the minima Fourier solution and the Kazoo complex associated to the functor, and that's very convenient. That's very convenient to have information about the functor itself. Great. So I'm now done with the motivation. So it has been a long way up to here, but this just to make just to connect to the main theme of the presentation, which is that not only upper semilattices do this job of fitting well in persistence, as I mentioned it in the introduction as well, but also realizations. We'll get there, a little bit more patience, because before I would like to introduce a notion of dimension of a point in a poset. Actually, two notions of dimension. The first one, we actually call it dimension of a point, which is very local, so it's a point-wise dimension. It's defined as the sup over the cardinality of some subsets that have some properties of being finite, having a common ancestor, and they have X as a sup. Sup just means for us least upper bound. I know it's not very standard notation, but that's what we call it for short. And moreover, this U should be the maximal one having X as a sup. On the other hand, you may define this other notion of dimension, which is called parental dimension. Is again a sup over some cardinality of subsets U, which this time are again finite, are inside the strict downset of X, have again a common ancestor, but as a different, X should be a sup of every two element subsets in this U. They, you might think about these two notions as complexities of expressing X as sup of its downset. Indeed, in both cases, you take X, look at the downset, and see what are some subsets of this downset having X as a coproduct and having some other properties. But I think that this is going to be better understood if we take an example. So the poset I now is this thing here that is actually a cube, just drawn in a different way. And we want to compute the dimension of the upmost point X. Well, then we might take these 3 points in the second layer and notice that however you take 2 points inside this set, you have X as a sup. And moreover, they have a common ancestor, which is this downmost point. So the parental dimension is 3. If you want to compute the dimension now of the same point X, we can see that the previous subset cannot realize it because it has not that maximality property that we were looking for. In fact, we took 2 points that had X as a soup. But if you take the second layer, then it has this property. It has a common ancestor here, and however you take 2 points, their coproduct is going to be, for example, take these two, their coproduct is going to be this one, so not strictly less than X. So dimension and parental dimension in this case are take the same value, 3, but they are realized by different sets. So this is the first taste of the fact that they have some differences. They are not completely equivalent.
And sorry, Francesca, I just
right.
want to make sure I understand. So
yep.
the subsets U, that has to have a common ancestor. Okay, all right. So yeah, so the condition is we're looking over U's that have an ancestor. And
precisely.
Then, right, and then
this having an ancestor is common to both definitions.
Yes.
The difference is how the soup, what X is a soup of, basically.
Are you going to show us examples where these 2 dimensions are different?
Yes.
All right, great.
Next slide.
Awesome.
Before, you might even wonder why we call it parental dimension, since there was no clue about it before. And the reason is that we figured it out before, we defined it before for finite type posets. Finite type posets are not exactly finite, but are those ones that have finite downsets for each point. So for example, n to the k. And in this case, the parental dimension is actually computed as the maximal subsets of the parent of the point, which has a common ancestor. And I know I've already used a lot the word parents, but I thought that was a good moment to highlight even more that this P of X really is the parents of X. So those ancestors that have nothing in between with X. So that's this proposition addresses just in questions, which is that the dimension is smaller or equal in general to the parental dimension of a point. For an example of strict inequality, you can take this poset, which for obvious reason we refer to as a suspension. If we want to compute the dimension and parental dimension of this point X, you may notice that the dimension is realized by any 2 points in the middle layer. So for example, these 2. And hence it is equal to 2. But the parental dimension is instead realized by these 3 points, because now it is a finite poset. So we just look at its parents, look at the maximal one that have a common ancestor, and we realize the parental dimension. So what's the takeaway with this dimension thing for now is that maybe dimension has a more straightforward definition and it's more natural, maybe. However, the parental dimension is way easier to compute because you just look at the parents in the case of finite type posets. And but that's not the end about this slide. I forgot, which is that. But the end is that if you take a finite type distributive upper semilattice, then the dimension and parental dimension are actually equal. And with distributive, I mean that exactly what you're thinking, that the coproduct distributes with respect to the product. However, one needs to pay a little bit extra attention about the fact that possibly products do not exist. So this equality should be read as if the two products on the right-hand side exist, then the product on the left-hand side exists and they are equal.
Mm-hmm.
So, great. I think it's half an hour that I'm talking, and I didn't tell you the definition of realization yet. That was planned, even though okay, you'll tell me later if it was a good idea or not. But the realization of a poset is defined in the following way. So you start with taking a point in your poset and define this R subscript A of I, which is not yet the realization, but it is the collection of pairs AF, where A is just a point in your poset, and F is a function that is defined on the parents of A and takes values in this half open interval -1, 0. This F has the following properties: that has a finite support, and the support has an ancestor in the poset. Once you do it for all the points of your poset, you take the union of this R subscript A of I and refer to it as a realization. All right. What does it mean? What are we doing? Well, this function can be thought of as a time to move from your point A to each of its parents. Again, if that's still not clear, here's an example. Take the easiest poset that you can, okay, not the easiest, but almost the easiest poset that you can think about, which is just XA, and X is smaller than A. In particular, X is a parent of A. It's finite. The arrow is just there to tell you what's the relation. Well, if we take now pairs of these points and a function defined on the parents, we might identify these 2 points X and A with X, 0 and A, 0. Now, the nature of these points is a little bit different, because for X, actually, we have no parents. So we artificially identify it with the 0 function. So it's more of a convention. But here, actually, we are taking A and give to its parents X the value 0, meaning that we are not moving from A, we are staying fixed there. Now, if we let F move, varies, and assume values that are non-zero, then we obtain the full segment here connecting X and A. In particular, if we would like, for example, to take the point in the middle of the segment and to characterize it in the realization, then this is going to be the pair A, F, which associate to X the value -half, meaning that we are moving halfway through in the direction of X. To fix even more the intuition about this realization, let's consider this other poset, just a nice one, in which there is A, its parents X and Y, and their product. Again, as before, we can take the points, we can realize the points in the realization and realize the segments between the points, but also we can fill in the square. How do we do it? Just take the middle point, then this is going to be realized by A, the function that associates to both parents, X and Y, the values -half. So that it means that we are moving halfway through in this direction and halfway through in this direction, ended up in the middle of the square. So to simplify, what does this realization do? It just fills in empty spaces that might be in a discrete poset. Now, this condition of having a finite support is rather a technical one. We need it for proofs, but this one is more a conceptual one, because we would like to not be in a situation where let's say that the poset is just given by the points, by these 3 points. The realization and this point on the corner as dimension 1 intuitively, and parental dimension 1. So in the case this condition was not here, then we would fill in this space with a square. But here we are transforming this poset into a poset of dimension 2, which is like not what the intuition would suggest us. So we just avoid this. In order to avoid this situation, we put this condition. All right.
If I may ask a question.
Of course.
So how is this realization related to the order concept? Geometric realization of the order concept.
I'm not sure I've understood. To the?
How is it related to the order complex?
To the order complex?
Yeah.
I don't know.
Okay.
Sorry, I don't know. I look it up and
Yeah, so Hans, by order complex, do you just mean like I look at chains and now I define a poset based on the chains of that poset?
Yeah, that's the typical thing to do.
Yeah.
But, yeah.
Yeah, and I suppose like yeah, I mean that doesn't necessarily need to be sort of continuous, whereas I think this construction just by allowing to have a continuous range of values for parents via the function f, that will have the effect of like kind of gluing in a cube of cardinality, whatever the number of parents is of each element is. Is that right?
yes.
All right, cool. Yeah, so it,
Yeah,
it almost
for
feels
example,
dual in a sense, but either way.
I don't know if that clarifies somehow, but might happen some weird things. For example, take the suspension. Its realization looks something like you have a cube. Okay, but it's kind of, no, I cannot draw properly here. But it is kind of, it has empty boundary, so it's kind of weird construction in some cases. Now I presented to you some nice cases in which you have a lattice, and so the realization is nice, but sometimes it's not very nice.
Maybe I can make a comment. Sorry, I'm
Yes.
cutting in. So the important thing is that this realization is going to be a poset. That it's not just a set or a space, etc. And of course, you know, maybe the realization of the, you know, the nerve of that poset might have the same homotopy type as the that you started with, which is the same as the homotopy type of the standard, you know, realization. But the important thing is the poset relation on this realization. Just sorry.
Yeah. So actually, yeah, Wojciech, on that comment, and Francesca, just want to make sure I understand. So if I have two functions on the parents of A, so is the relation, because I want to be able to say that this is a poset, right? So how is f less than f prime? Is it f less than f prime if f of each parent is less than f prime of each parent? Is that right?
Yes.
It's very complicated, and Francesca is maybe will
yeah, you know why it's complicated, but you got a very good point, because let's say that these two that you are in this situation, then how do you compare to functions that are defined on different domains? And that is actually, that was a huge issue for us to define this relation, that it turns out not to be intuitive at all. So you really have to write a lot, several conditions, and define it this way. So this part is easy because you just say that they are comparable if A and B are comparable in the poset. But the problem is with the functions.
And the most that was really, like, we did not believe at the beginning that it's possible. It took really a long time and a lot of lost hair to actually realize that it is possible. Another thing why you might suspect that it's complicated is because this realization, this set that as a set so far, Francesca defined, is not functorial construction. If you have a map of posets, you know, a map of posets can map elements, you know, parents not to parents. They could be very complicated, and you know, a priori as it is, and normally it is not functorial construction. And the fact that it is a poset was a big revelation for us. Okay, sorry, I don't want to cut in.
No worries. I was about to say exactly that. So it is not factorial. It is as a set contained in the Grothendieck construction in a Grothendieck construction, but it's not a Grothendieck construction. So it was a nightmare. And when Wojtek says that we didn't believe it, it means that I was very skeptical. He was always the believer. But indeed, Wojtek was right, because indeed it is a poset. So another thing that is interesting is that the realization of a poset is not in general, of an upper semilattice is not in general an upper semilattice, as it can be seen with this example. So the example is, I mean, I would be X, Z, A, B, C. Its realization is like this weird, continuous thing. But actually, it is not a good example, because this still, it's not its realization is still an upper semilattice. What I wanted to let you observe is that this thing is not an upper semilattice. So notice that it contains this poset that is non-distributive here, and also here actually. But its realization, I don't know how to draw it, but it's not an upper semilattice. However, if this distributivity assumption is taken, then we obtain that the realization preserves the upper semilattice condition. So yeah, this is still another clue of the fact the realizations behave a little bit weirdly, but they also have nice properties. For example, despite they are not, they do not preserve upper semilattices in general, they have this nice similarity with them, which is in particular, if you take a finite poset, you realize it, and you want to compute the parental dimension and dimension of a point AF, then they turn out to be equal. And in particular, equal to the maximal subsets of parents having a common ancestor, which also contains the support of the function defining the point. And again, this was something that we saw with upper semilattices not only for distributive upper semilattice, that these two notions of dimensions coincide. This is a first I mean, yeah, a first observation that made us think that these two approximations and realizations are kind of share more similarities than we might think. And
I want to maybe stress out that those are realization of any finite type poset. So I may not be distributed, it may not be an upper semilattice. So, you know, in I, the parental dimension and the dimension of points can be very different. Realize it, and realization works like regularizing your poset, because for realization, these dimension notions, you know, coincide. Sorry again.
No worries, that was an important comment. And another nice thing about realizations is that they admit some grid-like discretizations. What do I mean? The grid-like discretization that we denote with this RDIV, a bit not very compact way, but because it underlines the fact that it depends on a subset D of I and on V, which is contained in the open interval -1, 0. And it's finite. I forgot to write it here. This V is finite and this D also. And instead of looking at the definition, let's look at an example. Take the poset that we've already seen, this discrete square, and take D just given by the entire poset and V by these two numbers -1/3 and -2/3. We know how the realization of this square look like. It's just a full square. And this grid-like discretization has the property that the function, the pairs AF, only have values in V, which is finite. So we obtain this sort of grid inside the realization. And now you cannot avoid thinking about tame functors or persistence module, because that's exactly the sort of grids that you end up with when doing two-dimensional persistence. And yeah, this is not over, because these realizations are really telling you something about tameness as well. So this time we need to assume that I is a distributive upper semilattice, and take a tame functor indexed by the realization, which is then an upper semilattice again. We can say that then this tame functor is discretized by a grid with a diagram. That's what I'm saying, that this F is your tame functor. This is discretized by some poset, by some sublattice inclusion, actually, where this is a grid and this is a nice functor indexed by a finite thing. So we remember now how do a left-hand extension looked for upper semilattices. So in particular, if we want to compute F, the left-hand extension at some point AF, this is just going to be G evaluated at the coproduct of the downset of AF. Again, I have already told you that I like to draw pictures in keynotes. So this is an example. Say that you want to evaluate F at this point inside the square. Then you have your grid discretizing the realization. First thing, you consider the downset of such a point AF, which is made by these 6 red points. After you take the downset, you take the coproduct, so the maximal element inside this. And but now you may think, okay, but this is nothing special about AF inside this small square. And indeed, this left-hand extension is going to be constant inside this little square of the discretization. So another property that it shares with persistence module indeed. Great.
I have a quick question.
Yes.
So the what's the definition of tame being used here?
Again, left-hand extension of
Finite
of
stuff.
another functor that is indexed by something finite.
Okay. So yeah, because I wanted to make sure. So it's like I start with F. I know it is the left con extension of some functor indexed by a finite subposet.
Okay.
And then you're saying, well, now I can actually think of that that left con extension as actually the con extension along the inclusion of the sublattice.
What happens is that here I call it proposition because it is a proposition in the sense that, so in principle, just talking about tameness means that you have a left con extension or something like this, where this is finite, but it factors through a grid.
Nice, nice. All right, good, perfect.
But yeah, thank you for the observation. This is very important because it's not that you just define it to be discretized by a grid. It's like it actually theorem.
Nice. Yeah.
All right, but I'm almost done. This is my last slide, but it's very long. So,
we got 10 minutes, so don't worry too much.
Great. So because this like closed the circle, telling us what's the relation between tame functors, Kazoo complexes, minimal resolution, realizations, everything. So all the ingredients are inside this theorem. And it's the following. So take a finite type poset and a functor indexed by the realization of such a poset, and assume that is then resolvable, that we need it as an assumption, we don't have it for free. And assume that is also discretized by a grid. And this alpha is the inclusion. It's just that I was used for something else. All right, so if it happens that for a point AF in where the Betty diagrams of the functor F are non-trivial, if it happens that there is a epsilon inside V characterizing your grid-like discretization, such that the function F do not assume values smaller than epsilon, then these Betty diagrams of F at this point are isomorphic again to the homology of the Kazoo complex of F precomposed with the inclusion. So we can say that this is a nice condition. What does this condition contains is the following fact, that it implies that every parent who has a common ancestor has the product, which is the condition that, if you remember, we needed for in the case of upper semilattices, or even before upper semilattices. And the problem that might happen is this one. So let's say that you are inside your square, inside your realization, and you take a point AF that is in the support of the Betty diagrams. And however, this poset, underlying finite type poset, might not have a product of the parents. So it might happen that you are in AF and you can reach the parents, but then you don't know where to compute the product. What do we do in this case? Then we take a refinement of the discretization in such a way that from F, you can always go to the parents, and the parents have a unique product, so that we know how to compute the Kazoo complex and in this case. And this is not such a crazy assumption, actually, because if you have grid-like discretization, you can always take a refinement by taking a V prime, which just contains your V that is given, and this will satisfy the assumption of for which every parent having a common ancestor has a unique product. So to conclude, the second part of this theorem says that, in particular, if the Betti diagrams of a functor of this type at the point AF are trivial if the degree I is bigger than the parental dimension of the point. This might look like familiar because it's kind of resemble the Hilbert-Syzygy theorem, which just gives you a bound of the length of the minimal free resolution of your functor. And yeah, that's what I've just told you. So that we have a upper bound given the parental dimension of the point. So I'm done. I just, if this was really too much, I might have added a lot of material to this presentation, but I would like just to leave you with this takeaway, which is that upper semilattices share a lot of properties with realizations, even though it might not be expected. In particular, these properties are both combinatorial in the sense that, and I'm referring to the dimension and parental dimension, but also in persistence, since they kind of allow us to retrieve information in a similar way, homologically speaking, so about the minimal free resolution. In case I raised your curiosity, here is the link to it's not a link, but yeah, the archive number of the paper. If you're curious, just feel free to have a look at it or a part of it, because it's pretty long. All right, and yeah, thank you very much for staying until the end, and I'm happy to take any question if you have any.
Let's first give her a quick round of applause, and again, I want to thank Francesca for giving an amazing talk. I'm going to pause recording so that people can ask questions freely.